Hello and welcome to the Optimization of Powertrain Components with CAESES and CONVERGE webinar. This is Dan Probst and I'm going to give a short introduction. So CONVERGE is a computational fluid dynamics software with fully coupled autonomous meshing. It has a comprehensive set of physical models that make it ideal for engine simulations, including spray, combustion, emissions, and turbulence models. This simulation being shown here is a high-fidelity LES simulation of a heavy-duty gasoline compression ignition engine run by researchers at Aramco Research Center, Argonne National Laboratory, and Convergence Science. The CONVERGE simulation had over 100 million cells. Simulations like these are pushing the limits of engine research with CFD. The meshing capabilities of CONVERGE, which creates a mesh at runtime from a surface file, is particularly advantageous for optimization problems where the geometry is changing through optimization parameters. Recently, CONVERGE version 3.0 was released with significant enhancements over previous versions. Version 3 has cell-based load balancing and reduced RAM requirements to provide better capability on HPC clusters. The new version is more highly scalable, can better leverage fast interconnects, and can compete simulations with faster turnaround. The plot shown here compares runtimes of typical engine simulations with version 3.0 versus version 2.4, the previous version, on high number of compute cores. You can see here for real engine cases, the runtime for an engine cycle was reduced 60 to 75% in comparison to version 2.4 when run on a high number of cores. Because the engine cases can be run on large numbers of cores, the wall clock time for full engine cycles is reduced significantly. For the single-cylinder high-speed diesel engine case, we were able to run 16.5 engine cycles in one day, and for the spark-ignited PFI engine case, we were able to run 12.5 engine cycles in one day. Both these cases are run on an HPC cluster with a fast InfiniBand interconnect. These engine cases were not tweaked to make the parallel results look good. These are real results for best practice engine setups. These kind of turnaround times open the door to engine research applications that were prohibitively expensive in the past, such as knock or cycle-to-cycle variation, which require the simulation of many engine cycles, or optimization, which requires typically 1,000 or more engine simulations to identify a global optimum. This slide shows the many partners that we work with. If you are looking for additional tools that complement CONVERGE, please visit our partners page. Today's webinar will review recent work with geometry optimization with CONVERGE involving two partnerships with Friendship Systems and their CAESES software package and Aramco Research.
Thank you for this introduction, Dan. This is Mattia Brenner from Friendship Systems in Germany. And I would like to talk a little bit about our tool CAESES and how it can be used for specifically for powertrain applications in connection with CONVERGE's CFD tools. So let me start by giving a little bit of context. So the target of what we want to achieve is automation, and the reason for this is that due to laws and regulation and competition in the market, the expectation for the performance of modern engines is very high, and typically this is not easy to attain with, let's say, traditional iterative manual processes, but these targets can only be reached with optimization. And these kind of automated processes, which are optimization or automated design exploration, they typically lead to better and optimized designs. They can, of course, reduce the development times or reduce the design cycles. And also, which is a very important point in my view, they also increase the knowledge about how the product behaves very early in the design process. So gives an understanding of how the product reacts to changes in different parameters and creates a basis for decision making later on in the process. So if we want to run these kind of automated processes involving CFD, we need to involve several tools to run that. And first of all, we need a simulation tool that can provide the performance information that we would like to evaluate. This is done very nicely by CONVERGE. And we need a driver of the optimization process, so a tool that supplies all the algorithms and strategies that we need to run the different design parameter studies and explorations. But also a large amount of data is created throughout that process, so that the tool needs to manage all this data that we generate and also allow for some post-processing where we look into the actual data that we created and are able to make design decisions. And finally, the third component that is needed in this process is a suitable CAD tool that can produce all the different geometry variants that we want to analyze throughout this process. And basically the last 2 points are what we are trying to address with our tool CAESES. So as you just heard, one part of CAESES is a CAD tool. So you might ask yourself the question, why would I need another CAD system? So typically every company has already some kind of CAD system in operation. And due to our experience, the typical bottlenecks that people encounter when they're trying to set up and run such design exploration or optimization process are actually related to how the geometry is handled and how the variation of this geometry is handled. So typically with traditional CAD systems, while they might be very powerful for many different things, often don't have a strong point on geometry variation. So that part, when you're trying to automatically create geometry variants, change geometry parameters in an automated fashion, this is often prone to failures, so the geometry might break down, cannot be regenerated, or might need some manual work. So that's of course a significant problem. Another important point are constraints. So typically when we're trying to optimize the geometry, we have certain constraints to take into account due to manufacturing or packaging, for example. And that's also a point that's often not so easy to consider with traditional CAD systems throughout the optimization to make sure that the optimized geometry that we get in the end fulfills these constraints. Also, a bottleneck that is encountered from depending on the situation in the company is that there is a division of labor between the simulation engineers and the CAD department, and the simulation engineers are typically dependent on the CAD department to provide the geometry models and to create geometry variants due to some change requests. And of course, that's not very suitable for automation. And finally, last point, the quality of the CAD model might not be directly suitable for simulation, so cannot be transferred to the simulation system or the meshing directly as it is. There might be some issues with water tightness or even the level of detail that we have in the model. And yeah, these are the kind of things that we're trying to address with our CAD functionality within CAESES. So if we look a bit more closely at what do we do, as I said, our tool CAESES, the strongest part of CAESES is the specialized CAD tool, which allows to build up smart parametric models of the geometry, also efficient parametric models that allow a lot of variation, a lot of flexibility, but without having too many parameters, because if we have the more parameters we have, the more the effort for the optimization scales. And that is also very robust to run these variations. The second component that is included within our tool CAESES is the automation of external simulation. And this is basically where we have the interface to CONVERGE and where we can transfer the geometry from and other inputs from our system to CONVERGE and collect results. And the final component is the optimization environment that provides the algorithms, the data management, post-processing that I mentioned before to really run all this process in an automated way. So now let's come to how you can make use of CAESES specifically for powertrain applications. And I want to start with one application, which is at the moment probably the most popular application for CAESES in this field, which is piston ball design. So the capabilities of CAESES for piston ball design are that arbitrary ball profile parameterizations can be used. So there are no templates that are prepared, but everything is user defined, and you can define and come up with your own parameterization using the parameters that you want and giving you all the control that is needed. So you can see some examples here on the right side. The second point, which I mentioned already, which is, so to say, crucial point in our process, that we can allow robust variation of the geometry with mostly no failed variance, or at least very, very little failed variance. You can see some variation of the geometry here on the side. And in the context of piston balls, an important constraint is the compression ratio. Typically, when we're changing the geometry of the piston ball, we would like to keep the compression ratio to a fixed value. And this is something that can be involved in the parameterization, so that you can change the parameters that you would like to change and keep the compression ratio always fixed to exactly the value that is needed. Finally, when the geometry model is ready and can be varied, it needs to be exported for the simulation, and we support export in several different formats that are suited for the downstream CFD process or downstream CAD also. And in the context of CONVERGE, we support the native surface stat format that CONVERGE uses, where you can also identify different areas of the geometry with different IDs, so that they can get the appropriate boundary conditions and mesh settings and things like that. So now we've talked a lot about geometry, but through the interface where we connect CAESES to CONVERGE, we have complete access to the CONVERGE input files, and every value that is included in these input files can also be parameterized, so that the geometry variations and the investigations on this piston ball geometry can be combined with other parametric studies on injection parameters, for example, or other simulation parameters that should be changed. And finally, since we've seen just ball profiles now that are rotated for an axisymmetric geometry, it's also possible to create non-axisymmetric ball geometries, as you can see here on the side, different types. And basically, you can change the ball profile in a circumferential direction, or you can add additional features into the ball to allow, let's say, more experimental shapes. So a second application that I would like to focus on today is intake port design, which is probably equally important as piston ball design for the different types of engines. Of course, here you can also parameterize arbitrary types of intake ports. You see some examples on the side. And again, crucial importance is on the robust variation with no or little failed variance. Something that is possible in the way these geometries are parameterized is that flow relevant parameters can be controlled directly. So the parameterization is completely user defined, so it can be really tailored to the properties of the geometry that are of importance. Here, an example that is given here is the area progression in along the path of the port, including things like blocking due to the valve stem or valve bossing. It's also possible to consider constraints, for example, for manufacturing. Here we have an example for drafting angles. So typically, due to the casting requirements, we need to have some drafting angles at the side of the port, and these can be built directly into the model and also be taken into account during the variation of the geometry. An alternative to the parametrization that I talked about just now is morphing. So we also have the possibility to import existing geometries into CAESES and change these geometries using different morphing methods that are available. You can see here on the side a video of one of our morphing tools that allow for a very easy interactive definition of the shape changes. And this is basically a quicker approach than a full parametrization of the geometry, because it very quickly allows you to define some changes to geometry. The downside is that it gives a little bit less direct control on the geometry, and it's less flexible than a full parametric approach. So another important thing here for these port geometries, due to the cramped space in the cylinder head, are packaging restrictions. So here there is a possibility to monitor the distance of the port geometry that we're changing to neighboring components. So if you have your injector and bolting holes and oil gallery and things like that imported into CAESES, you can check all the distance to these components all the time while the geometry is changing, and make sure that minimum distances are not undercut, or that that there are no collisions between these components. And finally, similarly as for the piston ball, the geometry in the end can be exported in a CFD-ready format, which includes the definition and of different patches of the geometry that are included in the export format and that are available to be addressed in the downstream process. So these are two applications that I wanted to focus in more detail. Of course, CAESES can also be used for other applications in the powertrain field, for example, manifold, exhaust manifolds, intake manifolds, can also be used for cooling jackets. Here, typically, morphing methods are used to adjust the shape of the cooling channels. It can also be used for electric powertrain. Here, also, cooling is typically an issue that is addressed with optimization, or for details such as injector design. And if we move a bit further away from the engine itself, turbochargers are also very good and popular application for our tool, and that, so to say, gives also the transition to other more different applications in turbo machinery, such as pumps and gas turbines and steam turbines. Yes, so much for an introduction about our tool and the applications of our tool from my side. And now I would like to give over to Pei from Aramco, who's going to tell something about Aramco and how our tool CAESES is used there for combustion system design.
So good morning. Thanks, Mattia and Dan. So for my presentation, I'm mainly going to show how we leverage or using CAESES to support our engine combustion system design optimization. So my name is Yuanjiang Pei from Aramco Research Center, Detroit. So first, I want to acknowledge the contributors to this work, including my colleagues at Aramco, Yuanjiang, Jihad Bajra, Mengtang, Praveen Kumar, Michael Trevor, and also collaborators at Argonne National Lab, Pinaki Paul, O.P. Oyella, Sibinu Som, and also collaborators at French System, Casting Futura, and Mattia Brenner, and also Dan proposed Kelly, Eric, and Keith at Convergent Science. And also we have our technical inputs from the Advanced Engineering System Integration team at Cummins Technical Center. So the computing resources, we use a Mira supercomputer at Argonne extensively for our design work. We also have our in-house cluster basically doing the pre-DOE and post-DOE parts. So first, a couple of slides on our introduction of a company. Basically, our company is a fully integrated energy and chemicals company. So we are the largest oil exporter in the world. We also have a huge reserve on the natural gas as well. So over the past several years, we have been significantly expanding our refinery business. So overall, worldwide, we have more than 70,000 employees from more than 90 nationalities. So it's a very diversified environment. So over the almost past 10 years, right, we have been expanding our research footprint over the world. So in US in particular, we have 3 research centers, one in Houston, one in Boston, one in Detroit. So I'm located in Detroit. So our Detroit center mainly focuses on the transportation technology. So a little bit more information about Detroit. So we have a few research areas. One is in the strategic transportation analysis. Second one is the passenger transport, and third one is the commercial transport. So these passenger transport and commercial transport mainly focus on this innovative fuel and engine technologies. And then we also have vehicle technology integration. Basically, we're not going to just look at the engine part, right? We want to put an engine in the vehicle to really demonstrate the performance. So the safety part is mainly for following this passenger transport and commercial transport area. We're basically supporting different new engine concept development. So a little bit more details, right? So for the Detroit Research Center, we have 5 state-of-the-art engine test cells, fully automated, and we also have one 4-wheel climate chassis dyno to do this vehicle testing. Also have our own controller that's really important for us to explore different new engine concepts, then to do the really control the kind of to support the new concept. And we also have excellent computer capability as well. So for come to the real project. So this here we are using one example project to demonstrate how we use these cases to support our engine combustion system development. So basically, this is a heavy-duty gasoline compression ignition project. So I'm going to give a little bit background information why we're doing this, what's the motivation behind this. So if you look at this figure, it basically shows a fuel ratio of this middle distillate to the light in the fuel as gasoline. So basically, you can see from different sources, by 2040, you can see this fuel ratio of this basically diesel to gasoline could reach as high as 1.8, right? So this is a huge demand kind of imbalance. So this demand shift likely will produce like this price imbalance between the gasoline and diesel. So finding ways to effectively burn this light in the fuels in compression ignition so becomes very attractive. So this kind of one motivation we look at this concept. Another on the other side is this regulatory requirement, right? This is representing basically look at the timeline, look at the CARB kind of regulatory requirements. So kind of timeline looking to 10 years down the line. So you can see the NOx emission is going to be lower and lower, right? Maybe it's not final analysis yet, but it's kind of down the road, maybe 2027, 2028, the NOx could reach like a very low, like a 0.027 gram per kilowatt hour. So this, this kind of a very low critical pollutant emission kind of requires kind of a new kind of an engine concept coming in to meet this requirement, right? This is GCI concept basically offers kind of a better NOx soot trade-off, right? Kind of a potential pathway to meet this requirement at a relatively lower cost. So the test engine we have is heavy-duty, modern heavy-duty engine. It's very popular on U.S. freeway. It's a 15-liter, 6-cylinder, very efficient. The brake thermal efficiency is about 44% around that level. So it's a really popular engine and also kind of really well optimized. And any improvement above on it is really challenging. So here we use this test engine, try to look at different comparison ratios, look at different combustion concepts to see the potential of this engine using different fuels. So for the fuel side, we look at several different fuels, right? So we look at diesel fuel, that's the fuel for this engine. We also look at different gasoline fuels, basically 160, 170, 80, all the way to the market gasoline. So basically our strategy is that we look at, so chemically, first look at 160, chemically it's very similar to diesel. The city number is 34, close to diesel is 41. And then physically it's very different, similar to gasoline actually. So we then look at other gasoline as well to see what's the best or what's the potential there to look at different fuels combined to the engine. So we use an analysis-like design process. Basically, we start from CFD to basically give us some initial combustion recipe and air system targets. Then we go into the hardware development phase, basically do the optimization, the design, do the fabrication, and finally in the test cell we do the integration testing. Then based on testing results, we see compared to the feedback to the first CFD part, then we can to examine, okay, which part we're doing well, which part we still needs improvement. This is an iterative process, right? So in this process, we also work closely with our collaborators. For example, for the chemical cleaning part, we will work closely with the CAESES. They have some expertise, really good expertise in this area. Basically use that to refine our chemical kinetic part, and also machine tech using their constant warm chamber to help us to refine the basically provide high quality spray experiment data, including both diesel spray and GDI spray. And then we use the spray data to improve our spray models, and also work extensively with the Argonne National Lab on different topics, including in-nozzle flow, engine design, machine learning, ignition, various topics. Then work closely with our collaborator at Argonne to improve our sub-models. Then we also have our post-process toolkit in-house here to basically try to improve our productivity to efficiently support different projects. So basically we use this analysis-like design process for co-optimization of fuel engine to achieve robust full load range operations. So here is kind of very specific for the combustion system part, how we do this kind of flow process. So basically in the first box, we use CAESES, basically handle all design space, including all the design parameters and all the geometries. So, including the injector, intake manifold, pre-chamber, piston, spark location for cold start. So we use CAESES extensively to support this design space manipulation. It's very important. It really helps us streamline the process. Then after we got all the design combinations, basically in a CFD profile, a CFD file, right? All different designs, maybe like 100,000. So at different operating conditions, right? So it's very important we need to optimize the concept at different operating conditions, consider different scenarios. Then we use a Mira CPU computer at Argonne extensively. So Mira is a simple computer. It's like it's very gigantic. It basically has 800,000, almost 800,000 CPU cores, and then although per core efficiency is slower than a typical cluster, but it's basically has unlimited cores, right? You can run all these simulations at the same time, can significantly reduce the time to design. So also it's not a trivial job. You just run the simulation there, right? It actually needs years of research. Actually make the code here is especially for CONVERGE, make the code scalable, optimization or utilization of the I/O memory, lots of work. So Argonne and the Combustion has done significant work here to make the code scalable. and performing well, robust on the supercomputer. So after we got all the results, like in a relatively short time period, then we could move to the third box on the right, basically using a responsive model to get optimized design. Or in the meantime, we also using machine learning to see the further potential to reduce the time to design. That's kind of the basically a full process we currently have. So finally, we got the design candidates then delivered for design fabrication to finally put in test cell for integration and testing. So this is one example. We follow the process, right? This is for a heavy-duty GCI project. So first step, very important, we need to have a solid validation. You can see here at different operating conditions, different compression ratio for pressure curve emissions. We can have a pretty solid validation for different operating conditions. Then give us confidence to move to the design optimization. Then following the process, that's the fuel consumption improvement we got from the simulation, right? Up to 4.1% ISFC improvement at one operating conditions. This bar chart basically shows the improvement from different design parameters. Then finally, we got all the hardware and put in the engine for testing. So this is basically what we got. So we got up to 4.2% BSFC improvement from the experiments. So it's really encouraging results. Right now, we are working on to see, okay, which part we're doing well, which part we still need improvement. So at least bottom line is we got a really encouraging result. This kind of HPC basic design optimization method really reduce the time to design and deliver really encouraging results. So we also, like I mentioned, we also using machine learning to help us further reduce the time to design. Here, there's a couple methods. One is a machine learning genetic algorithm method. Basically, you can see from this plot, it's a very complicated surface, right? So you want to use the machine learning to kind of do this kind of data mining, right? So then, first example of this machine learning GA method, the plot on at the bottom, you can see for 90 different design parameters here, using a traditional CFGA method compared to this newly proposed machine learning method, you can see it's a pretty good results compared to traditional method. And again, this is give a much shorter kind of significantly reduce the time to design using the supercomputer while still achieving a really good results. And also there's a new method called machine learning gradient ascent method. And also we take this method to explore this geometry part. You can see there's a couple of applications here. One is for light-duty GCI gasoline compression concept. The other one is for heavy-duty GCI concept. So you can see there's a pretty good, encouraging results compared to traditional methods. So this is currently we already achieved, and also we in the meantime right now we're actually working on kind of looking at the more complicated designs like a full geometry, including all the real features, also like others injector and the pre-chamber, more complicated geometry. That's something we're currently working in progress. Hopefully that you can see it in the future of publications. Okay, I think that's it from my end.
So now I would like to take over again and quickly try to run you through a process of how CAESES is used for specific applications. So beforehand, I give it like a general introduction and about the capabilities, and now I would like to show how does it actually look if you want to work on a specific project with CAESES. And the example I have here is about the port optimization project. So the case that we have here is an asymmetric intake port for a diesel engine, and we're basically running it as a flow bench case. So we have a cold flow, no moving piston, but the flow comes in through the intake port and then goes out the bottom of the elongated cylinder, and the swirl is measured there. So this is one of the objectives that we're trying to optimize here. And also we have been looking at the so-called port permeability or discharge coefficient. So basically the amount of flow that goes through the port. So I would like to start with the modeling process. So if we want to work on such a case, the first step would be to build the parametric model to be used in the optimization with all the parameters that we want to be able to access and all the freedom of variation that we need during our optimization. And here we would like to model the part geometry, of course. And we start that by defining the paths of the two channels in the port. And this is the first path that we have designed here. And to give you some more detail, this is designed using two 2D curves. So basically we have the projection of the path onto two of the principal planes, and we parameterize these projections and then combine them to a 3D curve that is then the actual path. And then we do the same, of course, for the second channel of this port. And then we can place sections along this channel, and we have different methods of modeling such surfaces in CAESES. One option that one can use is to have a parameterized cross-section that is basically swept along the path or in a certain direction, and then during the sweep you can control the parameter values of this cross-section with a function that basically describes at each position along the path how the parameter value looks like. In this case, we have used a slightly different approach, which is using discrete cross-sections because it's somewhat more efficient for this port geometry. And we have created some cross-sections here for the first channel, as well as the same smaller amount for the second channel. And then we are able to use another type of surface generation to go through these sections. So it's a little bit like a lofting, but we have some additional control, especially because we want to control the tangency of the channels at the inlet and at the outlet. So using this special lofting technique, we create this channel and the second one as well. And then when we have the two channels, we can intersect them and create the fillet at the intersection or this septum between these two channels. And yeah, and the next step is to add the different other components that we have here that we also need for the simulation. So we have the flame deck here and the valve seats. And then we have the valve guides or bossings that are intersected or attached to the port channels. And then finally, we combine this with the valves. You cannot see the valve geometries now here in this picture, but you can see the cutout of the valve stem in the bossing. Yeah, and finally, we add all some additional components that we need for our CFD domain to run the computation. So we have this hemisphere, sorry, that's the correct word, the hemisphere at the intake inlet of the port to give the right flow distribution, and then we have the extension along the cylinder liner. So now I would like to just look at a few selected parameters of this geometry. Of course, the whole geometry model might have a number of parameters, which might be 20, 30, something like that. And I selected just a few to visualize how the geometry changes. The first one is basically the size of this fillet here in the septum. So you can see how this changes from a smaller to a larger value and back. And then we have another parameter here that controls the path of the first channel. So again, along the path, we have, of course, several different parameters that control its shape, and this is one of them. And similarly, we also have a parameter here visualized that controls the second channel. And then we have here a parameter which acts on the cross-section of the first channel. So basically, this parameter here is making it larger and smaller. So, and the same thing for the second channel. This just to give you an idea of some of the individual parameters. And now I have another animation here that shows a combined variation where we have involved several different parameters. I think it might be 10 parameters or so, and they're changing all at the same time in the same way as would happen if you run a DOE or design space exploration. And then you can see really the multitude of different shapes that are generated by changing all of these parameters together. So now we have the geometry model ready and the variability or variation of the geometry model ready. And the next step is to connect CAESES to our simulation tool, to CONVERGE. And this is done with the so-called software connector in CAESES, which is basically a generic interface where you can define all the data exchange between CAESES and the external program. So here in the first quadrant of this connector, we have we define the geometry export and the format and that we want to use for this export. You see here the picture of the final geometry we're exporting for this flow bench case, and that's exported as a so-called surface stat file for CONVERGE. The coloring that you can see here in the geometry is also related to the different IDs that we have assigned to the different patches of the geometry. And in the second quadrant here for the input to the external tool, we have all the additional input files that are needed, script files, simulation files, previous solutions, everything else apart from the geometry that you want to transfer to the solver. And here we have all the typical input files for CONVERGE. And in the bottom half of the software connector, we define all the results that we want to read back into CAESES when the computation is finished. And in the first quadrant there, we have the result files that are read into CAESES as a complete file. So this could be screenshots, for example, that are created externally as a simple case, but you can also import complete flow field data, tabular data, other things. And then in the final quadrant of this connector, we have the so-called result values, which is basically functionality to extract specific values from ASCII result files. So you can define at which position or search for certain keywords in those result files and then extract certain result values that we would like to use, for example, in the optimization as an objective function or as a constraint. So then we can bring at least in the preparation of the process before we run the actual optimization, we can bring the exported geometry from CAESES into CONVERGE Studio. And here you will see all the different IDs that were previously assigned to the different parts of the geometry in CAESES. So the colors look different, but the subdivision of the geometry is the same. And basically then here in CONVERGE Studio, you can address these different geometry patches and use them for different boundary conditions and things like that. So yeah, and then you have your case set up and you can run the computation. And then the next step is the post-processing. So as I showed in the software connector, we can read result files into CAESES, which can be used to extract individual values, but we can also import the complete flow field data, and we can create post-processing images visualization within CAESES directly. That's one option you see here, for example, with some streamlines. Or the other option is that you can also involve TechPlot in the process. So you can record a post-processing macro in TechPlot, and you can use that macro within the optimization process to automatically generate pictures for all the variants that are created during the optimization. And then we can read these pictures in as a result through the software connector into CAESES. And then in CAESES, when we're finished with our optimization run, we can look at all the results that have been created. There is, for example, table view to see all the different generated variants with their parameter values and their results. You can create diagrams and reports and so on from that. And you also have the possibility to compare the different variants side by side. You can compare screenshots that you have created in CAESES or externally, for example, in TechPlot, as I mentioned before. And you can also compare directly side by side the 3D geometries for all the variants. So you can rotate them all simultaneously and look at the geometrical differences between them and really dive into your results and make some design decisions at the end. So here, then finally, just for the results, in this case, just example, but to give you an idea of how the optimization process would look like, here we have started with an initial DOE to explore the design space. In this case, we're using an internal DOE algorithm in CAESES, the so-called Sobol algorithm. And then based on that DOE data, we ran a couple of following optimization runs. In this case, we used a surrogate model that was created with the data from the DOE and then refined with some subsequent CFD computations. And that will give you some view on the results in the end, like this Pareto frontier here, where we have plotted swirl against the discharge coefficient of the port, and this allows at the end to select suitable designs from this Pareto frontier that have a favorable combination of the different objective values that we're interested in, and based on the weighting that is assigned to the different objectives, different designs can be selected along this Pareto frontier. Yeah, this was a view of the complete process. That's so much from my side. Thank you very much. You can see some contact information here. If you're interested and would like to know more, you can get in contact with me through the email address that is shown here, or of course you can go on our website and find more information, and also another way of contacting us.
There are 2 questions. I'm not sure who they're directed at, but if you guys can just check your question box and determine if that's something we can answer.
Yes, there is just a very simple question that I see here that I can address directly. Someone is asking if there is a revision available for download, which I guess is the material from this webinar. I'm not sure if we will make the presentation material available for download, but definitely there will be a recording for this webinar that can be watched afterwards. So that's something people can address. There's also a question here if you can run multiple valve lifts for the intake port work. Yes, definitely you can do that. I'm not a big expert on the computational side, how that is addressed best with CONVERGE. What we can do on the CAESES side is definitely we can move the valve, we can create different valve lift positions, and feed these positions as different geometries to the solver. That's one option. Maybe CONVERGE has also some options to deal specifically with that, or
yeah, I can just take that a little further. So for this flow bench example, we're doing it at a fixed valve lift, and so CAESES could set the geometry up at multiple valve lifts, and then we'd run separate simulations for those, and it would be sort of similar to different modes for an engine simulation. So instead of different speed load points, we'd be doing different valve lifts, and then you could optimize your geometry to work very well at low lifts and high lifts, for instance. Along those same lines, there's one other question on this intake port simulation. The question is, why is the inlet boundary condition a hemisphere shape? The reason we do that is because this flow bench simulation is extending to kind of like a plenum, so a large reservoir. So we don't just do a flat boundary condition like on a port, like in an engine, go out to the hemisphere shape to try to capture the physics of that plenum. You could do that whole large plenum, but it would be a large cell count, and doing this hemisphere boundary condition gives you the same effect as the large plenum.
There is a question here. I'm not 100% sure how to answer that concerning the merit function, whether that is for one operating point or over the engine map, smooth engine map. So at least for the cases I have in mind and I remember, typically the objective functions were for one operating point, or you had several objectives for different operating points, and they were combined then into some kind of weighted function. I don't know, Dan, maybe if there's anything to add from your side, from the CONVERGE, if there is some possibilities there.
Yeah, I agree with that. The merit function, we do define that to be smooth and without discontinuities. So you want a well-behaved merit function, and having that for multiple operating points or multiple modes is something we typically do recommend. That question might have been during, I think that might have been asked during Pei's presentation on some of the Aramco optimization work. And that, if Pei can jump in here, but it was at different modes. It was like different speed load points, and that's what the B50 A25 signified.
Yes. Okay. So the merit function in the general form is similar. So probably just kind of a different operating condition depends on what your targets, right? You probably can have a different targets for different operating conditions. For example, the NOx target. But general form of the merit function will be consistent. Just kind of some specific targets for different operating conditions could be slightly different. No, I'm not sure if that's the answer. That's the question you're asking.
Yeah, thanks for adding that detail, Pei. I think that's good. There's a question, kind of a follow-up on what's available in version 3. So I think that what was just presented about CAESES was done in version 2.4, if I'm correct. But
Yes.
Version 3 will, as I kind of introduced at the beginning, version 3 is going to promise better scaling and the potential to run highly parallel during design of experiments or optimizations to reduce the wall clock pretty dramatically. So we're excited to be offering that with our release of version 3. The actual capability of doing flow bench simulations is available in both version 2.4 as well as the new version 3.0.
Yeah, I think that's also related to another question that is here by the same person, John, about the typical time for the optimization. I think that very much for a port, it very much depends on the computation time for each individual variant, and as you pointed out, then that's really helpful if the computations scale very well and are highly parallelized. Then that really helps with optimization, and so that depends on the specific case, but the optimization process, apart from the computation time, is also determined by the amount of variants that are analyzed throughout the optimization, and that's dependent on the number of parameters that we're trying to analyze. So just roughly speaking, to give some kind of idea, the typical optimization work that I have seen in industrial applications typically includes something like going from 100 to maybe 1,000 variants, depending on the case and number of parameters, and that, so to say, then scales with the amount of time for the computation. Not directly, because of course, for example, in the DOE, when you run just an exploration of the design space, you can also run many variants at the same time in parallel, which is also helpful to reduce optimization time. And then you can use surrogate models that also help to reduce that. So there are many moving factors that influence the overall time of the complete optimization task.
Okay, so there's one more question for CAESES. I don't know if you have time to take it. Do you see it, Mattia? That'll be our final question for the session this morning. Yes,
yeah, I can quickly address that. That's related to the unsymmetric or non-axisymmetric piston bolts, and how to achieve that. So we can parameterize any type of geometry. I mean, you've seen different applications here. So CAESES has generic modeling and parameterization capabilities. That's why you're not restricted to just making a surface of revolution for your piston ball with one profile. So for the non-axisymmetric piston bolts I showed, there we also use a parametric profile, but basically we change the parameters while we rotate the profile in circumferential directions. So that's one way of achieving that. Then you still have kind of a radially symmetric ball, but not a pure surface of revolution. And if you have other geometries that are completely asymmetric, then of course you can model them in a completely different way, not by rotating a profile, but rather using a different approach.
Okay, well, that's all we have time for today. Thank you guys for joining us. As Mattia mentioned, there will be a recording available of this sometime within the next week or so. Thank you for your time.
Thank you.